Hello and welcome back. In this video we're going to be looking at inverses of exponential functions, which we saw in the previous video, in the previous section. So let's review inverses really quickly. We can have a function f of x is equal to 3x minus 4, and we would normally graph this like the following: y is equal to 3x minus 4. And the inverse of a function is essentially when we switch the inputs with the outputs. So if we are switching the input, which is x, with the output y, we will have x is equal to 3y minus 4 instead. And we normally, when we're finding a function, we normally want to solve for y. So if I solve for y here, I could add 4 to both sides, and then divide both sides by 3 to get x plus 4 divided by 3. And this will be my new function, so if I call y my new function, I will have x plus 4 divided by 3. And if we think about this function up here, what are we doing? We are taking x and we're multiplying by 3 and subtracting 4. Well, if we want to undo this, we undo it in reverse. We add 4 first, and then we divide by 3 to get back to where we started from. So there's also some nice things about the graph here. So this graph will have slope 3, and it will start at negative 4. So if we start at negative 4, we go up 3 over 1. This is our graph of this function. When we flip x and y's, when we swap x and y's, all of our x values become y values, and all of our y values become x values. And the easiest way to see this is we'll start swapping our x and y values. Here we have a y value of negative 4. We'll swap that with an x value of negative 4. And then if we graph everything correctly, what we'll see is that we'll have some reflectional symmetry about this line. If we flip it over, we'll see that the graph of the original function, f, becomes the graph of the new inverse function, f inverse. So we've reviewed a few properties. A function only has an inverse if it passes the horizontal line test, and I'll go through that in a second. When we compose inverses, they cancel out. So up here we saw that my first function multiplied by 3 and subtracted 4. Here we added 4 and then divided by 3. So when they cancel out, we're just left with x at the end. And because we're swapping the x values and the y values, the x values that we can plug into f become the y values we can get out of f inverse, and the y values that we can get out of f become the x values that we can get out of that we can plug into f inverse. So the domain range switch. So let's look at our function here that we were looking at last time. This is an exponential function, and this certainly does pass the horizontal line test. If we draw a horizontal line, doesn't matter where we draw the horizontal line, it'll only ever intersect once. So this passes the horizontal line test, so this has an inverse. So let's try to find the inverse of this function. Well, we can go y is equal to 2 raised to the x power. So this is this graph here. And what I need to do is I need to switch the inputs with the outputs. So I need to switch the x's and y's. So I'm going to say x is equal to 2 to the y power. And next, I have to bring the y down out of the exponent to the bottom, because right now it's way up above the 2. And we haven't seen a method for doing this yet. We haven't seen a way to bring the exponent down, and this is actually quite tricky in general, but it is possible. We just have to define a new function. So what we do is we define what's called the logarithm. So the logarithm function is how we will bring a, let me highlight this in red, how we bring an exponent down out of the function. So if we have b to the y power is equal to x, and we want to solve for y, this, oops, I kind of cut off the b there. This is how we write this. So if b to the y power is equal to x, that means that y is going to be equal to the log base b of x. And these two equations mean the same thing. They are exactly identical. We've just written them in different ways. B to the y power is equal to x, or y is equal to the log base b of x. We've turned something with an exponent of y into an equation where y is not in the exponent anymore. So these two equations mean the same thing, and we read this as log base b of x. So the base is the same in both of these. Here, this is the base of the exponential. Here, b is the base of the logarithm. B is the base in both of these. So again, just to reaffirm this, in logarithm form, if we want to write something in logarithm form, write out y is equal to log base b of x. The same thing, if we want to write it using exponentials, is b to the y power is equal to x. These guys mean the same thing. So let's look at some examples. I have some logarithms here, and they're written in log form. We can see the logs here, and I want to write them in exponential form. So I want to rewrite these statements in terms of exponents. So we have 3 is equal to log base 7 of x. So the base here is still the same, and the way we write this is 7 to the third power is equal to x. These guys, again, mean the same thing. This is just written with logarithms. This is written with exponents. Here we have log base b of 25 is equal to 2. So this means that b raised to the second power is equal to 25. Okay? Both of these mean the same thing. So if I wanted to try to figure out what b was, and I felt that this was confusing, I could rewrite it as an exponent and go, oh hey, something squared is equal to 25. I have a couple of ideas what b could be here. And this last one, we have log base 4 of 26 is equal to y, which means 4 to the y power is going to be equal to 26. So in each one of these, we took a logarithm and turned it into an exponent. We can go backwards as well. We can take something that is an exponent and write it as a logarithm. So 2 to the 5th power is equal to x. So this means that 5 is going to be log base 2 of x. So again, 2 to the 5th power is going to be equal to x, so 5 is going to be log base 2 of x. These guys mean the same thing. Here, this base raised to the third power is 27. So I'm looking at a log base b, and I'm bringing the exponent down, so this is going to be 3 is equal to log base b of 27. And then finally, we have e to the y power is equal to 33. E, remember, is this nice number that comes up a lot with exponentials. We'll see that also because exponentials and logarithms are related, we'll see that e pops up a lot with logarithms. So this is going to be log base e of 33 should be equal to y. And I do want to mention a couple of restrictions here because it'll be important in the following. If we come back up to the logarithm function, the base of the logarithm, just like the base of an exponential, has to be positive, and it can't be equal to 1. So this is in the same way that when we're talking about the function f of x is equal to b to the x power, the same restrictions applied. So our bases can only be greater than 0, and they can't be equal to 1. So when we're talking about the log function, our base can only be greater than 0, and it can't be equal to 1. So let's look at a couple of examples and actually solve some numbers. So we want to evaluate the following. We want log base 10 of 100. And for this first one, I'm just going to rewrite this in terms of an exponential. So log base 10 of 100, I want to figure out what is this equal to? What is y here? Well, if I rewrite this in terms of an exponent, so this is going to be 10 to the y power is equal to 100. So if we ask ourselves, what power of 10 is equal to 100? Well, we know that 10 to the second power is equal to 100. So log base 10 of 100 is equal to 2. So another way to phrase this is 10 to what power is 100? And the answer is 10 to the second power is 100. Okay, so let's look at this guy, and let's rewrite this in exponential form again. So log base 5 of 1 over 125. So what we're asking is 5 to what power is 1 over 125? And here we can look at this and we go, oh, this is 1 over 5 to the third power. 5 to the third power is 125. Well, 1 over 5 to the third power, that's just 5 to the negative third power. So when we look at this, 5 to the y power is equal to 5 to the negative third power. It pops right out. Y is just negative 3. So log base 5 of 125 is negative 3. So here is our answer. We have log base 36 is equal to 6. So again, let's rewrite this in terms of exponentials and see what pops out. So this is saying 36 to the y power is equal to 6. And when we think about the relationship between 36 and 6, 6 is actually the square root of 36. So 6 here I can replace with the square root of 36. And we know that the square root of 36 is just 36 to the 1/2 power. Oh, hey, look. 36 to the y power is equal to 36 to the 1/2 power. Y is just 1/2 here. So log base 36 of 6 is equal to y. I just repeated myself. Log base 36 of 6 is 1/2. Because 36 to the 1/2 power is 6. This last one here, I want to, first of all, I want to rewrite this a little bit. So this is the seventh root of 3. Another way to write this down is this is the 1/7. This is 3 to the 1/7 power. So when we write this down, we're asking 3 to what power is the 7th root of 3? Well, it's 3 to the 1/7 power. So log base 3 of the 7th root of 3 is 1/7. So again, we can see that this is going to be log to what power is this guy here? Well, 3 to what power is this guy? 3 to the 1/7 power is that guy. So y is going to be 1/7. So the rest of this chapter is really going to be looking at properties of the logarithm function, and there are lots of nice ways, lots of nice things that pop out when we add logarithms, multiply logarithms, and a few special things about the number 1 and the number 0.